All right. Yeah, so welcome everyone. My name is Edward, and I'm joined by my teammate Shreyas. We're both software engineers working on RayServe, and today we're going to be talking about building production AI applications with RayServe. So high-level overview of this talk. So first, I'm going to talk a little bit about the motivation behind RayServe and how RayServe helps address some common problems that we see in serving online applications. Then we're going to dive into a few trends that we've noticed among the companies and open source users that we've been working with in 2023 and how we've been addressing them and some exciting updates that we've launched this year. And then for the second half of the talk, Shreyas is going to be giving a demo of running a production AI application on RayServe on the Anyscale platform. So that will show off a bunch of the features that I'm highlighting in the talk. So let's dive into the overview. So before I talk about RayServe, I first want to talk about some of the problems that we're trying to solve with it. So many of the customers and users that we've worked with come to us with an architecture that looks something like it is on the screen right now, which we call model microservices. So this is an architecture diagram of an application that has two models, one TensorFlow and one PyTorch. Each of those is a separate application with a separate Docker file, a separate configuration, and is deployed as a separate Kubernetes deployment. Those are then stitched together with some kind of business logic running in a Python web server like FastAPI. And as you can see, this works for deploying multi-model AI applications, but it's very complicated. There are many different configurations. There are many different code bases and images that you need to maintain, and this comes with some drawbacks. So the first is that it can be really hard to innovate. Because you have this single logical application split across many different components, it requires a lot of expertise, and there are a lot of moving parts that you need to update in tandem. It can also be really hard if you want to efficiently use and share resources among multiple different models. For example, if some models are used infrequently, and you want to have them share the same GPU, this can be really complicated to achieve with Kubernetes, maybe requiring you to understand the internals and the scheduler or use some kind of plugin for the cluster. So with RayServe, we're trying to build a better way to build these type of applications. So RayServe is flexible, scalable, and efficient compute for online inference. One of the highlights of RayServe is that, like the rest of Ray, it's Python native. This means that you can express complex applications like the one that I had in the previous diagram in just a single Python file. You can mix business logic with multiple different types of models, and you can iterate quickly, testing locally and deploying to production, all as a single program. We also have first-class support for multi-model inference. So this includes model composition, running many different independent models on the same hardware, and even use cases like model multiplexing, where you might have tens, hundreds, thousands, even tens of thousands of models that you want to run on a small amount of hardware. And overall, because RayServe is built on top of Ray, it supports flexible scaling and resource allocation, which is crucial for reducing costs, especially as the cost of hardware like GPUs rises. And of course, we're building this for online use cases, which means that it has to be production ready. And we've focused a lot on production readiness, with the two best ways to run RayServe being on top of Kubernetes or on top of the Anyscale platform, like you'll see in the demo later. So let's dive into a real-world example of these benefits. So here I'm talking about a user, Samsara, that we've worked with over the past year that changed their model serving solution to use RayServe. So before RayServe, they had separate microservices for this crash detection application. So the exact details of what's happening within each of these boxes aren't too important. The important part is that this anatomy looks similar to that architecture diagram that I showed 2 slides ago. They had multiple microservices in multiple languages, each with their own configuration, deployed independently, and they were stitching them together with HTTP. This came with some drawbacks. So the first is that it was inefficient, and they had a really hard time changing their parallelization and scaling strategy without rewriting a large chunk of modeling, infrastructure, and DevOps code. Any kind of innovation was difficult because they had to coordinate across these multiple teams if they wanted to change anything about their architecture. And this also meant that they had a high operational cost. Each of these was slightly different and was deployed, upgraded, and monitored both separately and in a slightly different way. So they ended up having a very high operational cost from all of the manpower they had to put into running this as a production system. So they decided to change to using Ray and Ray Serve for their next generation ML platform. They were able to express this entire application as just essentially one Python program, but with all of the flexible scaling and resource allocation benefits that Ray Serve gives you. This meant that they could make their application much more efficient. They could independently scale each step, they could parallelize within the existing steps, and they could share resources for different models and pre-processing stages. They were also able to iterate much more quickly in order to add new models, update business logic, and this was mostly because they were able to update their architecture and test it locally just as a Python program, and then deploy to production easily. And finally, this solution was production ready and gave them a unified story for deploying, upgrading, and monitoring the entire application together, instead of having a piecemeal solution with many different moving parts. So overall, moving from this model microservices solution to Ray Serve netted them over a 50% reduction in total ML inferencing cost per year. And this is not even including the benefits in operational overhead that I mentioned. This is just the hardware cost. So now let's dive into a few of the trends that we've been seeing in 2023 and how we've been addressing them. So the first, I think, is probably the most obvious. You've been hearing about this not only today, but probably ad nauseum for the past few months, which is 2023 has been the year of the rise of LLMs. Just a year ago, Shreyas and I were on stage at the previous Ray Summit giving a talk not too different from this one. And I don't think we said those 3 letters in a row. And today, you can't go more than like 5 minutes without hearing it. So the industry has definitely changed. So every week or 2 weeks, there's a new model or new techniques coming out. And the specifics of those are important. And there's a ton of business value being driven around LLMs. But to me, the more important point is this meta point, which is with technology changing this fast, it's just absolutely critical that you can iterate fast and keep up with the trends. You can't be locked into a framework. You can't be locked into an architecture. You have to be ready to actually be able to drive business value from these new developments quickly if you want to keep up. So in Ray Serve, we've been keeping up with the LLM trend, and the flexibility and the developer productivity of Ray Serve has allowed us to do that. We've recently launched the Ray LLM sub-project, which is optimized infrastructure for serving LLMs. And this is actually what powers Anyscale endpoints, which is the offering that you heard about in the keynote earlier today. This integrates with state-of-the-art solutions like vLLM for optimizations, and will soon integrate with NVIDIA's TensorRT as well. We've also added a number of LLM-specific features and optimizations, basically keeping up with the state of the art as quickly as we can. So this includes streaming responses, continuous batching, and tensor parallelism. And for a deep dive into this topic and some of the really cool stuff that we've been working on, I encourage you to check out Tanmay and Cade's talk tomorrow afternoon. So the second trend that's very closely related to this rise of LLMs is the increasing cost of hardware. So not only are models getting larger and more expensive, but there are also more and more use cases using machine learning. So as the hardware demands have gone up, GPU availability has gone down. I'm sure many of the people in this room have run into this problem where it's hard to even get your hands on a GPU to do inference or training. This means that more than ever, it's crucial to be able to efficiently use the hardware that you can get and make the most of flexible resource allocation and scaling and avoid wasted resources. We've been doing a lot of performance-focused work to address this year. One example of this is we recently launched support for model multiplexing, which is this case is for this many model workload where you have hundreds or thousands of models, maybe one for each product line or one for each user, which many of our customers have come to us with. And the model multiplexing support we've added to Ray Serve can more than double throughput on the same hardware for typical many model workloads. If you want to hear more in depth about that, I encourage you to check out our teammates Cindy and Sihan's talk tomorrow afternoon. We've also been working on some advanced auto-scaling capabilities to make sure that you can get GPUs as much as possible and at the lowest price possible. So on Anyscale, we now have support for cross-zone and cross-cluster or cross-region auto-scaling, so you can get GPUs wherever they're available. And we've also added support for spot instances for online services. This means you can use spot instances and gracefully fall back to on-demand when they get preempted, and will also automatically fall back from on-demand to spot when they become available. This means you can get instances for as cheap as possible. And this is one of the things that Shreyas will show in the demo in a few minutes. So with these techniques and a few more optimizations, such as the ones that I mentioned around VLLM and LLMs in general, Anyscale Endpoints, which runs on top of RayServe, has been able to offer state-of-the-art models like Llama 2 for 50% cheaper than OpenAI's GPT 3.5. And I also want to highlight some of the developer productivity benefits. The Anyscale Endpoints team has been able to add new models on the same day that they're publicly released, which is just really cool, and it's a testament to how beneficial it is to have to be able to locally test code and push to production quickly. So the final trend that I want to mention is that 2023 has really been the year that a lot of companies have gone to production with ML. In previous years, we'd seen a lot of POCs and ideation, but we hadn't seen people like really driving business value in production. But that's definitely changed this year. And what it means is that having a really solid deployment and observability story is just absolutely critical. You need to be able to sleep well at night when you're running these services. So we've been putting a lot of work into production readiness for RayServe and Anyscale services. We've added a lot of observability features over the past few releases, including the new Serve tab to the Ray dashboard and improved metrics and logging to help you figure out where your bottleneck is and what happened when things go wrong. We've also been doing a lot of continuous chaos and scale testing to make sure that we catch any stability issues before customers could even notice them. And we've been working closely with large-scale users to make sure that we improve the upgrade and stability story for both KubeRay in the open source and the managed Anyscale service offering. And this hasn't just been the year of machine learning going to production. It's also been the year of RayServe going to production. So as I mentioned earlier, Samsara was able to save 50% on their total annual inference costs by migrating their platform to use RayServe. Ant Financial is also running a 4,000 GPU online inference cluster, the largest one in their company, on top of RayServe. And Anyscale was able to launch their LLM endpoint offering and offer state-of-the-art models for 50% less than OpenAI's GPT 3.5. We've also seen wildly increased usage across the board. So across many different use cases and company sizes, we've seen over a 600% increase in the total usage of RayServe in the last year. So with all of the exciting use cases that we've seen people using RayServe going to production for, and all of the stability and feature improvements we've put in the last year, we're excited to announce that in 2.7, RayServe is now generally available. Thank you. So now I'm going to hand it off to Shreyas, who's going to give a demo of a lot of these cool features in action.
Nice. Awesome. Thank you, Ed, for walking us through some of the exciting trends that are happening in the ML industry and talking a little bit about how RayServe has helped propel those trends forward. Now let's jump into a demo that showcases some of the features of RayServe. So today we're going to be demoing a photographic calculator app. The way that this application works is you take a picture of an algebra problem, like 5x equals 10, and then you get an answer, like x equals 2. In between, we're going to be running two steps on top of RayServe. First, we're going to be running a reader deployment. This serve deployment is going to be running a PyTorch model, which takes in an image and then extracts text from it. It's going to send that text over to a solver deployment. The solver is going to be running SymPy. SymPy is Python's symbolic solving library. It can take in text of an algebra expression and actually solve that problem and give us our final answer. This is a pretty interesting application because the reader deployment and the solver deployment have very different hardware requirements. The reader is going to be using a CPU in order to load the image and do some pre-processing. But it also needs a GPU in order to run the model efficiently. On the other hand, our solver is going to be doing symbolic solving. This is a very CPU-intensive process, and our solver is not going to be using a GPU. Because of these different hardware requirements, it makes a lot of sense to split our application into two separate deployments. And as we'll see later in the demo, Serve can independently scale each of these deployments automatically in order to best meet your user's demand. Our demo is going to be running on the Anyscale platform. Anyscale is going to give us access to a cluster of Ray nodes. On top of these nodes, we're going to be running replicas of the deployments that we just talked about. Anyscale is going to provide access to that Ray cluster through a load balancer. So requests will come into the load balancer, get forwarded to the reader deployment, which will extract text, send that text over to the solver. The solver will solve the problem and send a response back to the user. We're going to be covering 4 different steps during our demo today. First, we're going to talk a little bit about the Anyscale service UI, which gives us nice visualizations for our Serve application. Then we'll go over Serve's new observability capabilities that give you information on how Serve is reacting to current changes in traffic. Then we're going to talk a little bit about Serve's new spot instance support, which lets you run your models and your workloads on top of spot instances to save cost. And last, we're going to cover autoscaling and talk about how Serve can scale the number of replicas and nodes in its system up or down in order to meet user demand. With that out of the way, let's jump into the demo. All right, so we're going to be starting our demo here on the Anyscale platform. The page we're looking at is the home page of our RayServe application. At the top here, we have the name of our application, our photographic calculator. We have some high-level information, like the fact that the application is currently running in production, and some other metadata. And right below, we have all the versions of our application that are running. We're currently running one version of the application with 2 deployments, the reader and the solver. Let's click into the docs for the reader and take a look at what they look like. All right, so the docs give us some information about the requests and responses that are going to flow through our application, but they'll also let us send a test request to our application, just to make sure that it's working. So let's try it out. As I mentioned, we have a photographic calculator. So I need a photo of an algebra problem. I Googled some algebra problems, and I'm going to take a screenshot of one of them and try to get Serve to solve it. We're going to screenshot this problem. 5x plus 4 is equal to 3x plus 16. So I take my screenshot, go back to the UI, and then I submit it. And then we let Serve execute. And down here in the responses, it looks like Serve says that x is equal to 6. Let's double check that just to make sure that we're right. All right, so again, the problem was 5x plus 4 equals 3x plus 16. On the left-hand side, 5 times 6 is 30. 30 plus 4 is 34. On the right-hand side, 3 times 6 is 18. 18 plus 16 is 34. Looks like both sides balance. Serve is getting that number right. All right. Woo! OK, so that was pretty cool. But now let's try to see what this would look like in production. What I'm going to do is start a burst of traffic against this application. Then we can use Serve's observability to see what that burst of traffic looks like. This is a terminal that contains a command which will start a tool that can generate load. Let's run this command. All right, we get a web interface. We're going to go over there to actually start the load test. All right, so this command is running a load test. On the first column there, you can see the number of requests that it's sending. It's sending requests just like that test request that we sent. And we can also see the number of failures. We see that the number of requests is going up. The number of failures is staying at 0. That's great. It means our Serve application is successfully serving traffic in production. We can also take a look at the requests per second that our load test tool is sending, as well as the response times. This corresponds to the throughput and the latency of our application. We're going to check back in on this tool in just a little bit. For now, let's jump over to Serve's observability and see how we might manage this application in production. We're back on the page where we sent the test request. Now, if I were managing this application in production, one useful feature that I might want is to understand how this request flowed through the application. For example, how much time did it spend on each deployment? So we can see in the response headers a request ID for this Serve request. I'm going to copy this request ID. And because I'm running Serve on top of the Anyscale platform, I can take advantage of a native integration between RayServe and AWS CloudWatch to quickly search through all of the logs that Serve is emitting and find the ones that are related to just this request. Let's go to AWS CloudWatch. All right, so we're in CloudWatch. CloudWatch is a tool that's going to aggregate all of my logs and let me quickly search through them. I'm going to search for any messages that contain the request ID for that test request that we sent. Let's hit Enter. Let CloudWatch look for the messages. Looks like no events were found on this one. So my mistake. I think I was looking at the wrong CloudWatch trace there. So what I'm going to do is run the same command. Over here. OK. Looks like CloudWatch still isn't showing anything. What could be happening is that the logs are simply delayed as the request is flowing through the system. But basically, what we would be able to see is any messages related to the request that we just sent. I'm going to try one more time. Oh, I see. Yeah, OK. We're not seeing any events from that particular message. But what we would have seen is basically logs that tell us the latency for the request at each deployment as it flowed through the system. Now, something interesting that we would have seen in those logs is that the request spent a lot more time on the reader deployment than it did on the solver deployment. This makes a lot of sense because, generally speaking, extracting text from an image is a much more lengthy process than actually solving the algebra expression. And this is also interesting as someone who's actually managing the application, because what that tells me is that the reader is the bottleneck of the application rather than the solver. And because of that, as Serve auto-scales the number of replicas and nodes in the system up or down, I'd expect Serve to create more problem reader replicas than problem solver replicas in order to best utilize resources and serve our users the best. So now let's jump over to some of the observability tools we have for Serve to take a look at how the application looks like from a higher level. All right, so I'm going to go back to the Anyscale console, and I'm going to go to the Ray dashboard. The Ray dashboard contains some useful information for our Ray cluster. And this year, we've added a new Serve tab that contains observability specifically for Ray Serve. At the top level here, we can see observability information for Ray Serve at a high level. For example, the healthiness of important Serve actors like the Serve controller or the Serve proxies, as well as the application status. We can also see logs in our application that gives us important information for what Serve is doing at any given point in time. And at the bottom, we can see metrics that give us high-level information about what's happening inside of our Serve application. On the left-hand side here, we see a metric for the QPS per application. And we can see that this has been steadily growing. This makes a lot of sense because we've just sent a quick burst of traffic. And that traffic is continuing to be sent to that Serve application. And we're seeing that reflected here in this metric. We also have any errors that are showing up in our application. We see no data because no errors are happening. Our application is successfully serving traffic. We can also take a look at the P90 latency for our application. Now, Serve also emits additional metrics on top of this. And if we want to take a look at those, we can click View in Grafana. Grafana gives us useful information for any metrics that Serve is emitting. It gives us dashboards that visualize those metrics and help us understand what's happening in the application. We can see some of the same metrics that we saw in the last tab, like the QPS per application, as well as the errors. And we can also see additional information, like the number of replicas for each deployment. Like I mentioned earlier, generally extracting text from an image is going to take longer than actually solving an algebra problem. So we expect to see the Serve application scale up the number of reader replicas versus the number of solver replicas. We can see that when we started the demo, we had 1 replica for each problem reader deployment and 1 replica for the problem solver deployment. But over time, we see that the problem reader scaled up to 6 replicas, while the problem solver stayed at 1 replica. This lets Serve process more requests in parallel during the reading step and save cost on the CPUs that are used for the problem solver deployment by solving it using only 1 replica. We can also see at the bottom here the number of nodes in the application. We can see that we started with only about 3 nodes, but then we auto-scaled up the number of nodes in order to provide more resources for the new problem reader replicas. Now, to step back for a second, observability is a really important component of any production-grade system like Ray Serve. But another important feature for production systems, especially this year, when hardware is becoming more and more scarce and more expensive, is cost effectiveness. So to that end, we've introduced spot instance support to Ray Serve. You can run your Serve applications on spot instances, and as Ed mentioned earlier in the talk, the Ray Serve will be able to adapt to any preemptions for those spot instances and shift traffic so that there are no failures. It'll be able to shift traffic onto on-demand nodes, and when spot nodes become available again, it'll be able to shift traffic back to spot instances to continue saving cost. So let's take a look at that in action. All right, so we're back on the Photographic calculator page. I'm going to navigate to the cluster that's running our Serve application. All right, so we're still in the Anyscale platform, but now we're on the page for the cluster that's running the serve application. This cluster gives us access to a terminal that lets me run commands on the head node of our array cluster. Now, for demo purposes, it's a little hard to guarantee that we're going to have a spot instance at exactly this moment. So what I've done is write a Python script that's going to simulate what happens when a spot instance gets preempted. It's going to send a signal to our serve application, and that signal is going to tell the serve application that a particular node is about to be preempted and give it an opportunity to shift traffic so that no failures occur. Let's go ahead and set the script up, go back to the dashboard, and grab a node that we want to preempt. Let's take this node. It looks like this node is running one of our problem reader deployment replicas and a proxy actor. I'm going to copy the node ID, go back to the cluster, paste it in, and we're going to preempt that node. It looks like the command is run. Let's go back to the serve tab on our array dashboard. We can see that all of the proxies are no longer healthy. One of the proxies has entered the draining phase. Draining is a status that indicates that that proxy is no longer accepting new traffic. It's just finishing up any requests that are still in progress. Because when spot instances are preempted, you get a 2-minute grace period before the instance is actually terminated. This gives the proxy enough time to finish serving all of its requests before the traffic needs to get shifted over to other nodes. Let's go back to the load test tool that we started at the beginning of this demo and see what the users would see when the spot instance gets terminated. I'm going to go back to that graph, to the table that shows the number of requests and the failures that we're seeing. We can see that we're still not seeing any failures, and the requests are continuing to be sent to the serve application. So in other words, no users are seeing any failures when the spot instance got terminated, but requests are continuing to be served. If we go back to the graph, on the right-hand side, we can see that just like we saw on the chart, there are no failures, but there's going to be a temporary dip in throughput until we've spun up a new node in order to continue to serve requests. I'd also like to point out one other pattern on this graph. On the left-hand side, we can see that initially we had a throughput of only about 6 requests per second. But we see that throughput has steadily gone up to around 22 to maybe 26 requests per second. This is because serve is auto-scaling. In the beginning of the demo, we only had about 3 nodes that were serving requests. But as we saw in the observability, we got more nodes and more replicas to serve requests, which increased the throughput. We can see the same pattern with the latency. We see that the latency, the 50th percentile for the latency was about 750 milliseconds when we started the demo. But once serve auto-scaled, that latency went down to about 160 milliseconds. So in other words, serve's auto-scaling was able to increase the capacity of serve and be able to service more traffic and do it in a cost-effective manner. So this brings us to the end of our demo. And just to recap what we covered, we talked a little bit about the service UI that the Anyscale platform provides for you to visualize the RayServe application. We went over some of Serve's new observability capabilities that tells you exactly what's happening in the RayServe application while it's in production. We also covered spot instance support and how you can run your models and your Serve application on top of spot instances to save cost in production. And last, we touched on Serve's auto-scaling. Auto-scaling lets Serve create new replicas and new nodes in order to service bursts of traffic without any failures. Overall, we're glad to answer any questions that you have about RayServe, and we'd love to talk a little bit more about how RayServe is GA in Ray 2.7, and we'd love for you all to get in touch with us on Slack, Discuss, or GitHub. So yeah, Ed, if you want to come on up, we'd love to answer any questions. Looks like we have about 30 seconds to do so. Yeah. You in the yellow?
Hi, in the previous presentation, we saw an example of how Samsara was able to migrate their Python Go framework into all Python, built on top of RayCore and RayServe, but not all times that the orgs is able to or can afford to migrate the whole system into another language. So in that case, what would you suggest be a better option, or is there any roadmap in Ray to support other languages?
Is my mic live? Can you hear me? Yeah. Oh, okay. Yeah, so RayServe actually does have experimental support for Java, and we're looking at adding more languages in the future. But we've also seen users that have just like piecemeal migrated part of their architecture to RayServe. It doesn't have to be all or nothing. For example, in that case, they could have taken just the Python parts and put that in a Ray cluster. So yeah, we don't have support for every language in the world, but those are 2 options.